Okay, in this video we'll go with a new topic, vector spaces. I already explained about the sets in my last video. The basic concept of sets you have to know. Now we will go with the vector spaces and vector space. First we will go with the new concept, field. I'm already saying this is second year course, so you will see lots of different things which you have never learned before. If you have any doubt about it, just comment me and I can explain with another video with this. But I'm presuming you know everything about first year algebra, basic linear algebra. So we will go with the new thing, field. So what is field? So for field, a field is a set F together with two binary operations. Which two binary operations? So it's addition and multiplication. Which are required to satisfy the following field axioms. Axioms is a thing which we don't have, we don't have any proofs, but it is. So let's assume we have x, y, z elements belongs to field F set. Field is a set F. So let's see now. We have set F. Let's assume we have set F. Its elements as 1, 2, 3, 4, 5. But let's assume first we will explain what is the field. So for the field, we have set F. When we can call it field, when that set satisfy all the field axioms. So the first axiom for the field is associativity. You have learned this before. Associativity is x plus y plus z is equal to x plus y plus z. This is for the addition. For the subtraction is x y z is equal to x y z. This is associative. This is the first axiom. The second one is commutativity. This is x plus y is equal to y plus x. This is xy equal to yx. Good. Third is additive identity. So we can say that exists. This is a quantifier. We have learned this in the previous video. The exists 0 and 1 belongs to set F. And we know 0 is not equal to 1, 2. So when we add, what is additive identity? When we add 0 in x, we will get x itself. Right? So this is 0 is our additive identity. So you have learned before in previous math classes, so not going much about this. For the multiplicative identity, this is t. Sorry. We can go x multiplied by 1 is equal to x, right? Y multiplied by 1 is equal to y. So identity is the thing, when you multiply something with 1, we will get that number itself. So this is the identity of that number. For the addition, when you add 0 in something, you get the same number back. So it's an additive identity. So after doing an identity, we can go with additive inverse. So for the additive inverse, we can say for all x belongs to f. For all the elements belongs to x, f that exists, minus x belongs to f, such that x plus minus x is equal to 0. When you add something in some number and when we get 0, then that number is the additive inverse of the number which we have added. Same we go with multiplicative inverse. For all x not equal to 0 belongs to f, that x inverse belongs to f such that x multiplied by x inverse is equal to 1. It's easy. I will go with an example and then we can go with together. Now the last axiom is distributivity. So let's go with distributivity. We have x multiplied by y plus z. Can write xy plus xz. Yeah, so this is distributivity. So in the set, if we have all these axioms in one set, we can say that that set is a field. Let's go with an example. So for the example, if we go with the big thing, it's set of all real numbers is a field. Set of complex numbers is a field. Let's go with an example. We have set f. As we have write the example on the top. 1 2 3 4 5. 1 2 3 4 5. So for the first we go with associativity. Yeah, you can go with associate like 1 plus 2 plus 3 is equal to 1 plus 2 plus 3. 1 2 multiplied by 3, you can go with 1 multiplied by 2. So yeah. Now commutativity, you can go with any number like 5 4 5 also, but just to make the video simple and good. Additive identity. Do we have 0 in that thing? Nope. So this is not field. So we will not go further about it. If we have 0 in f, if we have, then for sure f is filled. So question, no. Why? Like we go with f, we have 1 2 3 4 5. So for the additive identity we have to add 0, right? Then we jump with multiplicative identity, we have 1 in it, so we are good with that. Now we can have to go additive inverse. So in the f we have to add minus 1, minus 2, minus 3, minus 4, minus 5. We have to add all this too for additive inverse. For multiplicative inverse we have to add 1 by 1, so 1 is good. Add 1 by 2, 1 by 3, 1 by 4 and 1 by 5. For the multiplicative inverse distributivity, it's good. So when we add like all this, let's assume we have said z, it is minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1. No, with 0 we will go with like sending all. So 0, 1 by 2, 1 by 3, 1 by 4, 1 by 5, 1, 2, 3, 4, 5. Yeah, this set z is filled. But with this one, now we will go with a new concept: vector addition and scalar multiplication operations. Vector addition and scalar multiplication operations. So for first, like we have a set v be a set, and we fix f is filled, right? Vector addition operation on v is a function that assigns an element x plus y in v to each pair of element x y in v. So vector addition, like this is a vector a, this is a vector B. So this is A. Assume this go to B. So yeah, like this.
You'll need to unlock your iPhone first.
We are good with this. Now we have scalar multiplication. So this is A. If we multiply 2A, so it will be double then. Like we have 2A together. So we will go with an example with this. But this is, yeah, we have to know vector addition and multiplication. Now we will go with a new topic, Cartesian and spaces. So let's assume let n be a positive condition. We have n as a positive integer. So what is Cartesian and space? So it's a set of all ordered n tuples of the real number. This is what Cartesian and space is all about. We'll go with an example. This is all like basic concepts. I will upload a definition notes or definition video soon, which will include all of this together. But now we will go with this Cartesian. This is a Cartesian and space. R, we have A1, A2, go to AN, and we know that A1, A2, AN belongs to real number. So first we will go with vector addition in this. So we have one set A1, A2 up to AN. Then we have another set B1, B2 up to BN. So the vector addition will go like A1 plus B1, A2 plus B2 to AN plus BN. Same with the scalar multiplication. You can go R, A1, A2, AN. No, R belongs to real number. So it will go with a new vector now. RA1, RA2 going to RAN. Go with now polynomials. Same polynomial, in which polynomial it's a set of all polynomials of degree less than or equal to n with real coefficients. So let's assume, I will just go with an example. We have this polynomial a0 plus a1x plus up to an xn. So a0 going up to an belongs to real number. We'll add a vector addition in this one. So vector addition, it's a0 plus a1x plus going up to an xn plus b0 plus b1x plus going up to bnx. So how we will add this? So it will go a0 plus b0 plus x, a1 plus b1 plus up to plus xn, an plus bn. We will go with elements each by each, going the same scalar multiplication. Same thing, r a0 a1 going a1x going up to an xn. We'll multiply all things, r a0 plus r a1x going up to r an xn. Good. Now we are going with the third matrices, like we have done with Cartesian and space addition and multiplication. We are done with polynomial addition and multiplication. The matrix we will go to the next video. For this one, just this only. Thank you.